In this video, we're going to explore LLM training. We're going to rethink how it works and the geometry of it. This video is based on a paper. This video is about this paper. We're going to look at in detail different pieces of it and look at what it's trying to explain or share. And it's called Rethinking LLM Through Information Geometry and Quantometrics. What's great about this paper is that it uses the language of tensors and curved surfaces and manifolds, things you would find in general relativity, to look at what's happening during training phase of an LLM. And we're going to look at what probability distributions are and manifolds. So I'll build on the topics from the ground up. And lastly, we're going to look at what's great about this paper is how it connects quantum mechanics, Hilbert spaces, to LLM training. So there's a lot of deep, intricate connections that this paper makes. This paper is about a new and a different way of thinking about the geometry of LLM training. So the first thing that this paper talks about is that many large language models rely on first-order optimizations such as stochastic gradient descent and its variance. So let's look at what that means. So suppose you went into like a transformer and you were to give it some context. Suppose you asked it a question like the sky is, and it takes the sky is text and converts it into tokens through a tokenizer. And what this does underneath the hood is that there is an embedded matrix that was created when it was trained. And what it does is that it basically it does an embedding lookup and maps each token to a vector in this vector space. So each of them gets mapped to a vector. And when you look at it collectively, it creates an input sequence where each variable in this input sequence is a vector in the vector space. So then what happens is that then we take and give this to an LLM and it produces a probability distribution. It tells you the likelihood of the next token, what that will be. So all of these words are the vocabulary size. So it gives you the probability of each of them, and all of these should add up to 1. So this is the probability distribution that it gives. So what is a probability distribution if we look at it closely? A probability distribution is basically a parametric function where you have theta that represents basically the different weights. So this paper begins to talk about the probability distribution in a much more mathematical way. And it starts by defining something called a statistical manifold. So when you are training an LLM, all of those, your weights are changing, they're being configured. And what's interesting is that you're actually, if you think about it geometrically, tracing a path where you're starting from a random initialization. So let's look at, closely what this means. Let's start by looking at probability distribution. We know an LLM creates a probability distribution. We have these different probabilities for each element in the vocabulary of an LLM. And how do we look at this from a mathematical perspective? From a mathematical perspective, you to think of it as a function where V represents the vocabulary of an LLM, and it's assigning a probability from 0 to 1. So a probability can be from 0 to 1. So this is looking at it from a mathematical perspective as a function. But now, how do we take this forward? So this is the vocabulary. How do we take this forward and map this and take this idea and think about a probability distribution? So when you look at it mathematically, the way a probability distribution is constructed is like this, where you have a function P and you have parameters that you provide to it. And the parameter that we're providing to it is the context, like what your conversation so far, what you have written, the context that we're providing to the LLM. And for example, this is going to be the sky is. The next thing that you're providing are parameters. These are the learned parameters that are there, the weights that are in your LLM. And you're providing these weights. The outcome, the probabilities are based on the configuration of these weights. So this is a probability distribution. And what you provide also is a list set of tokens to this method. So you have what you have in this function is the tokens, you have the context, and you have the parameters. So this is a probability distribution. Depending on how training goes, you could have different probability distributions, and when you collectively take a step back and look at this, you could introduce the idea of a manifold, a statistical manifold. And this paper talks about a statistical manifold. What is that? So a statistical manifold. So first the question is, what is a manifold in itself? When it's not statistical, if you look at it in a general context, a manifold is a set that has a structure on it. It's a set of points, and you could take a point, an open set U. If I take a point P, and I could create a chart from this manifold to RD, and D is the dimension of the manifold. So this is a very much general idea of a manifold. This manifold isn't curved or anything like that. This is a very, very general idea of it. And we could take this idea of a manifold and apply it to LLM training. And the way we do that is by looking at statistical manifolds, because we're dealing with probability distributions with LLMs. So it's appropriate to use statistical manifolds where each point is a probability distribution P. And you may start in your training, for example, the point P could be a probability distribution where your weights are randomly initialized. And as you go through training, you are forming a path from P to Q. And Q, for example, assume is when you have completed your training and you have landed upon a set of weight parameters that work. So what you have done is you've gone through different stages of training through gradient descent is you have traced an arc on this manifold from P to Q. So this manifold, the question becomes, is it flat? Is it curved? And that's where things get interesting. So when you look at in an LLM training, the manifold itself is very much curved. There are hills and valleys, and how you navigate these hills and valleys tell you what's happening to the parameter. You could get the geometry is telling you so much about how sensitive it is, the parameters are, or how insensitive they are. So you may start at some point where you have a random initialization of the parameters in the beginning of your training. And then you get to some valley in this manifold, your target region, where you have fully trained basically your LLM. So what's interesting about this, if you take a step back, is that this is the mathematics that you see in general relativity, for example, where you're dealing with curved spaces. This is like the math from differential geometry and Riemannian geometry that you could utilize here. So we're looking at LLM training from a much more rigorous mathematical framework to understand it. And it has good, really, you could think about really nice implications that this has. One of them has to do with the Fisher metric. So this paper then talks about optimizations and geometries in LLM. It talks about what are the tools from information geometry that provide a richer picture of the underlying optimization landscape. And what does that mean? So when we look at our landscape, as I told you, we're starting off with some random initialization, some point, a probability, and we're starting off with a set of weights of parameters, which is what theta means here. And we're training, and then in our training, we're going from this probability distribution to another one. So suppose I wanted to, I'll show you a very, very simple toy example. Usually, you have a probability distribution where you have a lot of weights, you have a lot of parameters, and depending on the size of the dimension of the LLM. And here's an example, a very simple example of a probability distribution with two parameters. And how does that look? So we may, in our training, as we're training and going through gradient descent, and we may go upon a stage where our parameters have been updated. So we're at Q. So P, you started off with theta 0 and theta 1. As you train, you went to Q. So suppose that this change could be described by a vector displacement. That's what d theta is suppose this is a very, very simple example. Suppose there was a change in your parameter in your training by this amount. Now you could ask the question like, how sensitive did your parameters become, or insensitive that they became? And this gets into the idea of how do you calculate distance in this manifold. As we're training, how do we calculate the distance from P to Q? Well, different ways to do it. And all the different ways, they give you a richer picture about what's happening. So though this is a formula that that's used to calculate distance, is Pythagorean theorems, very, very simple. And what it is that you have your displacement vector, you have a transpose of it, and you're doing a multiplication with m. M is the metric tensor. And then you have d theta, which is what we saw before, your displacement vector. So the metric tensor, this goes back into the idea of tensor calculus. This is what you will see when you're studying black holes, for example. You have the Schwarzschild metric, the Kerr metric, and all these metrics are telling you how do you calculate distance. It gives you a way to calculate angles and distance. And each of the components in this metric tensor are telling you about how the space is stretched and curved. And as we use different metrics, they tell us different things about our training space. And that's what we're going to look at. So let's start with something that's very simple, which is going to be your Euclidean metric. So this is what you would use in flat space, and this is just the identity matrix. So, and when we use this for M, suppose we were to do this calculation, we get 0 0.1, 0 0.2. So it didn't really change anything about the displacement vector. It didn't stretch or shrink anything. And we are assuming that space is flat, that our training space is flat. And as we multiply it by the transpose of this vector, we get a specific distance. Now, the question then becomes, is this accurate? The problem is that this isn't accurate because if you look at our space is curved, and we're not taking that into account. Our statistical manifold has curvature. There is a Riemannian metric that it has. It's not giving us an accurate picture, and that's one of the things that this paper argues. So if you look at the distance, what's something else that we could use? We could use something that you'll find in information geometry, a different metric, which is a bit more complicated, as you can see. It's called the Fisher metric. And this Fisher metric, this is a Riemannian metric, and it takes into account the curvature. And when we do this calculation with the Fisher metric, it gives us a much, much more better picture of what's happening, how our weights are changing. So if we were to take the Fisher metric and do this calculation, we get a much more accurate number, 0.115. So if we look at the Euclidean distance, if we look at the Euclidean metric, it gave us a much, much more larger number. So what the Fisher metric is telling us is that we moved less far in distribution space, and we moved in an insensitive direction in our training. And the Fisher metric, as you can see, gives me much, much more valuable information about what's happening as we're in our training space. So And when the Fisher metric, when the value is high, when you get a high value, what's happening in our weights is that as we're training and we're making small changes, what that means is that our probability distribution is making big changes. The small changes in the weights is equating to big changes in our probability distribution. And what this really means is that as we're training geometrically, we're going to a sensitive region where distributions are easy to distinguish. So it gives us that insight about the geometry. But what if our Fisher metric came out to be low? If it's low and we're training and we're making small changes in our weights in our training, what's happening is that our probability distribution is also making small changes. And what this means geometrically is that we're going into an insensitive region where distributions are hard to distinguish. And that's what we want to avoid. So you could see there, this metric gives us much more richer information, but the downside is that it's very hard to calculate this practically. And what this paper talks about is this paper talks about something much more easier than the Fisher metric, and it transitions to quantum mechanics, the math of quantum mechanics that we could use. So if we take a step back, the Fisher metric measures how much the distribution changes when you change the parameters slightly. As you can see, it gives us a much more richer information. So in this paper, the Fisher metric is prohibitively expensive for modern architecture, so that's a challenge. By contrast, quantum systems inherently evolved on curved manifolds whose geometry is covered by another metric called the Fubini study metric, which is much more easier to calculate. And this paper is arguing that because this metric is easier to calculate, not less expensive, it gives us a much more richer information about the training space that we could use. So this paper, like now, bridges the gap. It goes from talking about information geometry, but now, interestingly, we could connect it to Hilbert spaces, which is the mathematics that you would find in functional analysis and also in quantum mechanics. So a Hilbert space is a vector space, and where each element in that vector space, Hilbert space, is a quantum state vector. So we could map it, model it to a quantum state vector. So Hilbert space, for example, is made up of quantum state vectors. And how do we utilize this idea with our classical view of LLMs? So when you look at an LLM, you have a probability distribution that is giving you. This probability distribution, each of these probability distributions in the vocabulary, each of these probabilities, which is for an element, each element in the vocabulary of the LLM, they all could map to a basis vector. That's what this is, a blue, cloudy, and red. We could map these to basis vectors, and we could formulate using this we could get a quantum state vector. And the way this looks like is this. We take these probabilities and we have to calculate the amplitude. So we can, so 0.5, 0.4, 0.1, we're taking the square root of that because we're trying to calculate the probability amplitude. So in quantum mechanics, in Hilbert spaces, we don't work with probabilities directly. We work with their amplitudes. So, and what this forms is a quantum state vector. This is a very simple example of a quantum state vector where you have a set of basis vectors. And this is a very simple example. You obviously, in a full-fledged LLM, have much more basis vectors here. Each vocabulary forms a basis vector because it defines the number of dimensions of this Hilbert space. So coefficients are the individual probabilities. So we have a quantum state vector. Now we're going to talk about quantum manifolds. So this, we are bridging basically from statistical manifolds to quantum manifolds. And what this is that imagine you had a probability distribution. Before, we looked at a statistical manifold where P, the point P, is representing a probability distribution. But in a quantum manifold, the set P is a quantum vector, is a vector, quantum state vector. And in the statistical world, as we're training, we are forming an arc, a path, a trace of a path from in each stage in our training. We're going from P to Q, going from random initialization to some final state of our parameters in training. And but it's very, very different in a quantum manifold where we're not basically drawing an arc. It's something very different. We're not drawing an arc. The geodesic, the shortest path, is very different in a quantum manifold. So in a quantum manifold, the one thing to note is that this is not really the curved surface that I showed you. This is a unit sphere. And this is a hypersurface, and it's hard to visualize that. And I'm not, it's hard to visualize that. I'm not even trying here. I'm representing this hypersurface as this blob, but you should know that it's a unit sphere in a Hilbert space. So we have these weights, and when the weights are changing, what's happening is that as these weights are changing, what's happening is that our vector is rotating on this quantum manifold. Now, as our vector is rotating on this quantum manifold, what we need to do something equivalent to measuring the distance to get information about our how these parameters are changing. What is the metric that is used that we could use? And the metric that we could use to measure distance is called the Fubini metric. And as this paper talks about, this is a snippet from the paper, and it talks about quantum systems, however, implement their own optimization geometry intrinsically. They do not approximate the curvature, they embed it. So what that means is that if we look at this quantum manifold, we have this quantum state vector A, and as we're training, we're going and rotating this to a quantum state vector B. And how do we calculate this angle between these two state vectors? So we could use the Fubini metric. And this is an equation from the paper. And what we need to do is to calculate the state vectors and look at their overlap. So you could do a manual calculation here and do a comparison of this will give you radians, for example. This will give you radians. And this is the metric that you could utilize in this manifold, in a quantum manifold. So if we look at both of these, you'll find that the Fisher metric is much, much more harder to calculate. And this paper argues that the Fubini metric is much easier to calculate, and it gives you a much, much more richer understanding of the geometry of training. So these are the highlights of things that this paper talks about, and I recommend reading it. Shout out to Ricardo Di Supio, and this paper is called Rethinking LLM Training Through Information Geometry and Quantum Metrics. What's great about this paper is how it connected the math you see, for example, in general relativity, where you're dealing with curved surfaces, and the math in quantum mechanics, which is where you'll find like Hilbert space. And it's interesting how it took a very classical view of LLMs, and it painted a very different picture, looked at it through a different lens, and gave you a richer understanding of it. So this is a theoretical paper. I recommend it. And these are some of the things it talks about. And I want to thank you. You could check out my website and my YouTube channel here, where you learn about not just about LLMs and how they work internally and papers. You'd also could check out content about Kotlin, Compose, and also physics. And that's about it. Thank you so much.